I'm working on 2 fuel cell prototype cars with various partners, Oxford University included. And what I have to say is based on one assumption, and that is that we want a sustainable transport system. And I believe that requires some very big changes. Having lived in a capital-based system for so long, in which we have the luxury of drawing down capital at any rate we like, albeit for a limited timescale, it's quite a big adjustment to develop a revenue-based system. The great benefit of a revenue-based system is that it goes on indefinitely, but the rate at which we draw it down is limited. And so if we're really serious about a sustainable system, energy efficiency actually becomes the dominant metric that we've got to be pursuing. Now, cars today are the most mature industrial product in the world, I think. I don't think there's anything remotely comparable in terms of value for money that you can buy. But they're no longer the products that we actually need. And as they are on the plateau of development, incremental improvement of the technology is not capable of meeting our needs. Furthermore, I'd suggest that just as modern cars have been optimized around combustion engines, the delivery of personal transport to society is highly technology specific and optimized around the cars that we actually make. However, I'd just like to preface everything I've got to say by saying I don't believe that the principal barriers are technical. They're to do with people, politics and business, and so I don't underestimate the practical difficulties that the industry has in doing what I believe is possible and about which I'm going to talk. However, if we aren't clear about our destination, we certainly aren't going to get there. Now, a fuel cell is not equivalent to a petrol engine. If we think in Venn diagram terms, they are fuel cells and combustion engines are overlapping ellipses. A fuel cell does some of the things a combustion engine does. It converts fuel into usable energy, for instance. But it doesn't do some things the combustion engine does, so there's no kinetic energy at the end of the fuel cell. On the other hand, it does do some things that the combustion engine doesn't do. And, for instance, it obviates the need for a transmission system. But because there's no direct equivalence between the components, we can't insert fuel cells incrementally into cars that are designed around combustion engines. You can't cross a chasm in 2 leaps. And the consequence of trying to make it behave like a petrol engine is that we stretch the technology beyond its capability and thereby create barriers to fuel cells being implemented. Now, the main barriers to this approach are the cost, the power density and hydrogen storage density. And to continue on this strategy, we have to go back to basic science, and we find that these objectives are not happy bedfellows. Increasing the power density and hydrogen storage density is very expensive and slow, and we find that they're therefore fighting the goal of reduced cost, but you achieve greater power density with more components, pressure, greater stress on the materials, more expensive materials, and so on. But as a consequence of all this, the efficiency drops of the system, and so the accent on the hydrogen storage density increases as well. An alternative strategy is to accept the limitations of the technology as it stands at the moment and seek resolution to all these conflicting objectives through design. And that way I believe that we can unlock advances and step changes really quite quickly and cheaply. If the vehicle performance can be achieved with existing technology, which I'm going to go on to in a moment, it becomes apparent what I mean when I say that these barriers are really artifices of the design approach that we are conventionally adopting. Starting off with the vehicle architecture I'm talking about, I start off with decoupling of constant and transient demand. A conventional car has a maximum constant demand of less than 25% when it's cruising on the motorway, and so you could say that 90% of the time it's carrying 75% of redundant powertrain and some other associated components as well. If we use regenerative braking and recover that energy to use 75%, to satisfy 75% of our acceleration demand through the regenerated braking energy, it allows you to decouple the size of the fuel cell from peak demand and just size it for the constant demand. However, that principle only works if you have highly efficient regenerative braking. Otherwise, the load levelling system is simply incapable of meeting the demand for acceleration. Maximising the regen efficiency implies that we never use friction brakes unless we can possibly avoid it. And assuming we have credible stability in braking performance, we do need four-wheel drive. The significance of the regen braking, and I think this is very important, is not that we save a bit of energy and use it again. The significance is really in the implications for powertrain sizing. The same applies actually to the structure, because the weight of the structure is largely dependent on the heavy bits that you have to hang on to in accidents, for instance. If you have a smaller prime mover, eliminate transmission system, as the vehicle weight drops, the power requirement drops further. And then there are some other step gains to be made in that contact patches of tires become smaller, so you don't need power-assisted system for steering and braking, for instance. And these iterative loops have become known as mass decompounding. We call this architecture a network hybrid, because every component in the powertrain, that's all four motors, the load levelling system and the fuel cell, are all connected to each other, and energy can flow in either direction on any of those paths, except back into the fuel cell. So, by reducing the power required, the power density is actually easy to achieve with existing technology, with cheaper materials and fewer components. So that's cost decompounding, if you like. The fuel cell becomes more efficient. The vehicle level efficiency is also higher, and so the hydrogen storage problem is eliminated by virtue of using less hydrogen rather than increasing the storage density. This is an illustration of the life car, which Malcolm McCullough's going to talk about later, but it's based on this approach, and the chassis is being shown at the Grove Fuel Cell Show next week. It's part funded by the DTI, and it's a partnership between my company, Oscar, which is responsible for the design concept and the integration, Morgan, who are providing the vehicle platform, Oxford, who are developing the electric motors and all the power electronics, Cranfield University, who have done all the computer modelling, simulation, and developing all the control algorithms, Kinetic, who are providing the fuel cell, and BOC, who are providing the refueling system. Models are currently showing that in the combined cycle it should do something around 150 mpg in petrol energy equivalence, and that in a car that does 0 to 60 in 7 seconds. Now, I wouldn't go so far as to say that the vehicle architecture I'm talking about is a magic bullet that's going to solve our sustainable or unsustainable transport problems. And clearly we've got to address the imbalance between mass and personal transport. But I also believe that the business strategies by which we develop serve the transport sector are just as technology specific, based around the cars that we purvey, and we need a similarly radical approach to redesigning those systems. But we need the whole basket of all these initiatives. We need some complementary policy and cultural shifts as well, if we're going to get there. I'd like to point out that whole system design is what I've been talking about at the car level, and it does yield completely different solutions to those that one would arrive at through optimizing subsystems. None of the elements that I've talked about make performance or economic sense on their own, yet the end result does. And the delivery system needs the same approach, and I'll give an example of one Aikido strategy, as some they have been known, one that yields the desired outcomes without great force. It closes loops, it's self-regulating, so it eliminates the need for active regulation. And I'd also say that a lot of our work is based on, I believe that we need to shift our focus from profit to resilience. You can't have a resilient system without profit anyway, so the profit remains an implicit requirement, but you can easily have a profitable system without any resilience. The example I'd like to talk about is moving from the sale of product to the sale of service. In a manufacturing business based on the sale of product, more profit is generated by the sale of more goods. And to be blunt, with the proviso that we all have competitors, and on the other hand they do have the same drivers, that equates to a direct financial driver for products to be as expensive as possible, as unreliable as possible, as high maintenance as possible, as short-lived as possible. The ownership cycle would be as short as possible, and there's no direct interest in energy efficiency. Now, all those are rewarding resource maximisation, which is actually the opposite of what we're trying to achieve. So it's not a highly efficient way of achieving our objectives. In contrast, if we embed a sale of service model at the heart of the process, designing vehicles that remain as assets on the manufacturer's books, the direct financial incentive is for the car to be as cheap as possible, as reliable and low maintenance as possible, because the manufacturer is responsible for maintaining it. The car to last as long as possible, the customer to keep it as long as possible, and the cars to be as efficient as possible because the manufacturer will pay for fuel. This brings the formerly opposed interests of manufacturers and society into direct alignment, rewarding what we're trying to achieve rather than the opposite, which does seem to be a more efficient and effective strategy. There's quite a few ramifications that come out of this. As I said, the drivers don't remain intact unless the asset remains on the manufacturer's books. He needs to have a driver to design for longevity, recyclability, etc. And now that the industry is rather less vertically integrated than in the days of Henry Ford, it means that the sale of service must be extended upstream as well as down. Otherwise, the suppliers would have the same opposing interest to the manufacturers as manufacturers currently have to consumers. This has the incidental benefit of further reducing the entry barrier for fuel cells, purchase price, because nobody's actually buying them, and returning the end-of-life value, which is a far greater value to the fuel cell manufacturer than anybody else, back to the manufacturer. It also distributes the very significant working capital requirements across the whole industry, net of any profit, and it allows access to second-hand markets through OEMs, which is would be quite an attractive proposition. I say that it's all inherently self-regulating because there's a constant incentive for manufacturers to reduce energy consumption per mile, or per mile of service delivered, if you like, and also the life cycle cost. But even more appealing is it flips longevity from being a problem into being a source of competitive advantage. If you can lease a car for 16 years rather than, this that's just taken as a nice easy number, rather than 4 years that is the maximum desirable for a conventional car at the moment, it means that you can harness the same number of revenue streams with 75% less productive capacity. It also reduces recycling liabilities and so on, but it does mean that the car can be more expensive, the manufacturer can take a greater margin, and yet it can be cheaper to the consumer. It also ultimately has a direct impact on the design choices made. I mentioned the impact on fuel cells and how it reduces barriers there, but for instance, we all know that composites are highly expensive, but it's even plausible that it'd be more profitable to make a composite car than a steel one, even if the customer pays the same amount. If we evaluate the whole system level, by building a car out of composite, it would be considerably lighter, and over the life of a 16-year revenue stream, it would save a dramatic amount of fuel, and so it might actually return a greater profit than the marginal cost of the composite body in the first place. I think that's enough. I hope it's been of interest, and